In this lesson, we'll talk about classification of systems of linear equations, as well as graphic solutions to systems of equations. What is a solution of a system of equations in x and y variables? Well, since we have two variables, we need to know both of them to have a solution. So the solutions for systems of equations will be ordered pairs x and y that will satisfy all equations in the system. Therefore, the solution set is the set of all possible solutions x, y that satisfy each equation in the system. Let's look at this example. First, we need to be able to check if a point given by an ordered pair of numbers is a solution to the system or not. For example, is the point A with coordinates -4, 2 a solution to this system? If it is, it's supposed to satisfy both equations. So what does it mean, satisfy? It means if we plug in the values for x and y to each of those equations, the equation is supposed to be true. Let's see. 2 times x. X is -4, so it's 2 times -4 plus y, which is 2. Is that equal to -6? Is this true? Well, we have -8 plus 2. Yes, it is -6. So yes, this point satisfies the first equation. But that doesn't make it solution to this system of equations yet. We still need to check if the second equation is satisfied by this point. Well, let's see it. X, which is -4, plus 3 times y, which is 2, is that equal to 2? Okay, we have -4 plus 6. 6 minus 4, yes, it is 2. So it does satisfy the second equation. Therefore, A is a solution. So we can give the answer. A is a solution to this given system of equations. Let's do the same for B. Is B a solution or not? Okay, since we need some room here, let's erase our previous calculations. And now we'll talk about point B. So that's our x, that's our y. Let's plug into the first equation. That will be 2 times 3 plus y is -12. So is that equal to -6? 6 minus 12, yes, it's -6. So this equation is satisfied by the coordinates of point B. What about the second equation? We have x, so it's 3, plus 3 times y, which is -12. Is that equal to 2? We have 3 minus 36. Oh, it's definitely not the same as 2. So even though point B satisfies the first equation, but it does not satisfy the second equation, that makes it not a solution. We can say B is not a solution for this system of equations. Okay, so let's summarize. To solve a system of equations means to find all possible solutions. In example 1, we just check that A is a solution, but how do we know if there are no other solutions? We didn't actually solve this system, we just check if those particular points are solutions. However, to solve a system means to find all possible solutions. That is, all ordered pairs x, y that will satisfy all equations in a system, or all points in a plane that belong to all graphs of the equations. Since in this lesson we are talking about linear equations, then the graphs of them will be lines. Therefore, solutions of a system of linear equations will be the intersecting points of the lines representing the given equations in the system of coordinates. How many solutions a system of two linear equations may have? Well, that depends if the two lines representing the given equations are, for example, parallel lines, then we don't have any solutions because they don't intersect. Or the two lines may cross each other in one place, that will be one solution. Or possibly the two equations represent actually one and the same line, so the two lines are actually covering each other. Therefore, every single point that belongs to one line will belong to the other line as well. In this case, we'll have infinitely many solutions. So we may have 0 solutions, 1 solution, or infinitely many solutions. We may classify those systems. The first classification is with respect to the solutions. If we have solution, at least one, then such a system will be called consistent. For example, this situation and that situation. Here we have one solution, here we have infinitely many solutions. Such systems are called consistent. Otherwise, if we don't have any solution, the system will be called inconsistent. So again, consistent if we do have solutions, inconsistent when we don't have solutions. And there is one more classification with respect to, are we talking about the same line or different lines? If the system actually describes the same line, like in this case, it will be called dependent. The lines depend on each other, they are going together. However, if the lines are different, such system will be called independent. So on our diagrams, the first two situations represent independent systems. The two lines are different. So we need to be able to determine what kind of system do we have. But remember, this classification applies only to linear systems of equations. Don't try to classify if one of the equations is, for example, quadratic and the other linear. You must have two linear equations, then you can talk about this classification. Let's try to solve and classify the following systems of equations using the graphing method. That means graph both lines and see where they intersect, if at all. Okay, let's graph the first line. Since the easiest way of graphing is to have our equation in slope-intercept form, let's rewrite it y equals negative 2x minus 5. I just brought the 2x to the right. Okay, so we have y-intercept negative 5, which is here. And since the slope is negative 2, we can see it as negative 2 over 1 or 2 over negative 1. In this case, 2 over negative 1 will serve us better just because our graph paper ends here. So let's go backwards. One step backward and two steps up. One backwards and two steps up, and following point. So we need to connect those points. Let's do it. That's our line. We should make sure that we have some scale here. One unit horizontally and one unit vertically. Okay, let's look at the second equation. I'm going to use green for this line. So this time we can use x and y intercept method for change. Why? Oh, just because I see that 6 is easily divisible by negative 1 and by 3, so our x and y intercept will be easy to calculate. If x is 0, then this part disappears, and then to solve 3y equals 6 for y, it will be 6 divided by 3, so it's 2. So 0.02 is our y-intercept. The future line comes through this point at 2. And secondly, if y is 0, then this part disappears and x becomes negative 6. So another point, negative 6. Well, it's not visible on this graph, but let's predict it will be here, negative 6. So these 2 points need to be connected. Okay, let's do it. Here it is. Now, from this graph, we can read that the common part, the point that belongs to the blue and to the green line, is here, and it has coordinates negative 3, 1. Therefore, the solution set to this system of equations is one element set. It consists of the pair negative 3 and 1. Okay, let's try the second system of equations. Again, the first equation I will graph in blue. Let's rewrite this equation in a slope-intercept form. I'm thinking of bringing the y to the right to make it positive, and bringing the negative 1 to the left, so it will be 3x plus 1 on the other side, 3x plus 1. 1 is our y-intercept, so it's here with the scale 1 on each axis. And the slope is 3, so we go 1 across and 3 up, or 1 backwards and 3 down. And again. And now we're ready to connect. Here's our line. For the second equation, I will use green, similarly as before. And again, let's try to solve it for y. So if my 2y will go to the other side, but I will write it here, and the 2 will go to the left, so it's 6x minus 2. we may notice that all coefficients are divisible by 2, so let's divide the whole equation by 2, leaving us with 3x minus 1. Oh, that's very similar to the blue line, but in the blue we had plus 1, in the green we have minus 1. So what we do, we start with the negative 1 on the y-axis, that's our y-intercept, and then the slope is the same as in the blue line, 1 across 3 up, so the next point is here, and over there, and backwards it will be here. Okay, let's join those points. Here's our green line. As we see, they are actually parallel. Why? Well, because we have the same slope, so the steepness is exactly the same. Okay, so what's the solution set? Since this time our lines do not intersect at all, the solution set is an empty set. There's no solution for this system. Finally, the last example. Again, let's solve the first equation for y. To graph it in blue, that will be negative 2x plus 5. We start with 5 on the y-axis, and we go with the slope negative 2, meaning 1 across, 2 down, and again, and again, and again. Let's join them. Here's our line. Okay, let's look at the second equation. Observe that all 3 coefficients are divisible by negative 3. So by dividing by negative 3, we could make this equation a bit easier to work with. So that will be 2x plus y equals negative 15 by negative 3 is 5. And then if we rewrite this in a slope-intercept form, we obtain exactly the same line as above. Okay, so we still have the y-intercept 5 and the same slope, negative 2 and negative 2 and negative 2 and so on. So the second line is going exactly on the top of the first line like this. Well, therefore, what are our solutions? Basically, every point that belongs to the green line is also a solution of the blue line. Therefore, the solution set is this entire line. Every single point is a solution. Okay, how can we record this solution set? If we just say that we have infinitely many solutions, well, that's great. We know we're talking about one and the same line. But can we go one step farther and try to actually describe those solutions? Well, we can use set builder notation. We can say the solution set is the set of all ordered pairs x and y such that the y satisfies this condition, one of those lines. So we can say y equals negative 2x plus 5. That will be enough to clarify what kind of points we have in mind. There is infinitely many points. It's enough to take an input x and calculate the y according to this formula to find a pair of numbers that will satisfy both equations. Notice that we can't just say all possible x and y ordered pairs, because that will represent any point on the plane. We don't take any possible point, we're taking any point from the line, so the y-coordinate is connected, is related to the x, by following the formula of one of those lines. Another way of describing the set would be to say we have in mind all ordered pairs such that x is independent, can be anything, but y variable in terms of x could be written as just negative 2x plus 5, because that's what y was. Okay, so that's another way of describing this infinitely many solutions. Finally, let's classify the above systems. So what can we say about the first system? We do have a solution, so the system is consistent. And the lines are different, so the system is independent. In the second example, we have 2 parallel lines and we have no solution. No solution means the system is inconsistent. The lines are still different, so the system is still independent. Finally, we have a system with lots of solutions, so it's consistent. But the 2 lines are exactly the same, so they depend on each other. The system is dependent. So graphical methods of solving systems of equations are probably the most appealing, we see at once do we have solution or not. However, they are not very reliable, because if we have exactly one solution, sometimes it's not easy to rate what are the particular coordinates. Specifically, if they are fractional, we may not be able to rate them from the graph. That's why in the next video we'll learn how to solve systems of equations algebraically.